All right, guys, welcome to the first lesson in Unit 10. Unit 10 is all about solutions and solution chemistry. So the first thing you got to know is that this unit has a lot of vocabulary in it. So a solution implies a mixture of some sort, okay? So we're talking about two or more substances being physically mixed together, not chemically combined, okay? And there are two types of mixtures in this world: homogeneous mixtures and heterogeneous mixtures. We talked about these terms a little bit at the beginning of the school year, like Unit 1 or maybe 2. So this should be a little bit of review. Homogeneous means the things that you are mixing are evenly mixed, okay? That there's a uniform composition through this mixture, okay? Like if you dissolve the lemonade powdered mix into a gallon of water and you stir it up and you stir it up and the lemonade powder all dissolves, that would be a homogeneous mixture. A heterogeneous mixture means a physical combination of things where they're not evenly mixed. Okay, for example, like vegetable soup has a mixture of different things and it's not the same composition all throughout. If you took a scoop of vegetable soup from one side of the pot and another scoop from another side of the other side of the pot, they would not have the exact same composition. A homogeneous mixture is the same thing as the word solution. Okay, they are synonyms. So from now on, I will probably use the word solution rather than saying homogeneous mixture because it just takes too long to say. So just a couple of examples. Solutions are typically something dissolved in something else. And, some examples from your everyday life. Example of a gas dissolved in a liquid. Carbonated water, or any carbonated beverage of any kind of soda. I wonder if any of you know what the gas is that's dissolved in soda. It's carbon dioxide. Okay, that would be an example of a gas being dissolved in a liquid. A liquid being dissolved in another liquid would be vinegar. Okay, we've talked about vinegar a little bit before. If you go into your kitchen cabinet and pull out the vinegar, vinegar is acetic acid dissolved in water. That's a solution. Okay, this sounds a little bit odd. A solid dissolved in another solid. An example is steel. Okay, steel is primarily made up of iron, but steel has small amounts of carbon dissolved in it, mixed in it. Okay, and it is a uniform composition. So these are just some examples of solutions, homogeneous mixtures. A little bit of more vocabulary here. If you ever see the word suspension, okay, this is a type of mixture where the particles will remain mixed, but only with stirring or shaking or agitation. Think of some examples in your everyday life of things that you shake up before you use them. Okay, things that settle over time. Like if you buy, a jug of chocolate milk and you let it sit for 24 hours in your refrigerator, when you go to pull it out of there 24 hours later, the chocolate typically settles to the bottom. So what do? You shake it up before you pour yourself a glass of chocolate milk. That's a suspension. Orange juice with the pulp. You shake it before you pour it. That's a suspension. Okay. Two very important vocabulary words here: solute and solvent. The solute is the thing being dissolved. Okay, the solvent is whatever you're putting it in. So for example, if I dissolve sugar in water, sugar is the solute, water is the solvent. Okay, a lot of these words I'm repeating a lot of the same thing again and again. The word soluble, if I say sugar is soluble in water, that just means it will dissolve. The opposite of soluble, insoluble. Something does not dissolve. Okay, sugar will not dissolve in oil, for example. Okay, so it's just a lot of vocabulary here. The word miscible is similar to the word soluble, but it's a little bit more specific. It means a liquid or gas will dissolve in another. When we use the word soluble, we usually are talking about a solid solute, like table salt is soluble in water. Miscible is usually like a liquid in another liquid. Alcohol is miscible in water. They will dissolve in one another. Water is immiscible in oil. They will not dissolve in one another. Okay, so there's just a lot of vocabulary there. Now, something that's important for you guys to understand, and those of you that go on to take AP Chem, this will become really important. Okay, we're going to talk a lot about ionic solutes. Ionic compounds are going to be soluble in water. And it's important for you to know what really happens physically, what happens in the process of dissolving. This graphic that's in front of you is a little bit different than the one that is on the notes that you have hopefully in front of you. But they represent the same thing. You have this ionic solute, this crystal of sodium chloride, table salt. The process of dissolving is basically just tearing that solute apart, breaking those ionic bonds and separating the ions, isolating all the ions. And I want you to notice on the image in front of you on the screen, at the top, the sodium ion, that positively charged cation. Look at the waters that are surrounding it. And that is really what happens. When an ionic solute dissolves, the solvent particles form almost like a cage around each ion. And I want you to notice that the water molecules, the oxygen side of the water is facing that cation. And if you guys will remember, water is a polar molecule, meaning a molecule where one side is a little bit more negatively charged, the other side is more positive. The oxygen side of water has a slight negative charge, which is why those oxygen sides are facing that cation. Remember, opposites attract. Look at the image on the bottom. The chloride ion is an anion. It's negatively charged. Notice that the water molecules this time have the hydrogen atoms facing it. The hydrogen side of water carries a slight positive charge, so it's going to be more attracted to those chloride anions. So that's what the dissolving process physically looks like. Okay, that's actually what happens. Now, what determines what will dissolve what? Well, there's a phrase that we use in chemistry, like dissolves like. What does that mean? That means polar solvents, like water, water is polar. Polar solvents will only dissolve polar solutes. Okay? I want you to maybe add something, maybe it's in your notes, I'm not really sure. Polar solvents, like water again, will also dissolve ionic solutes. Okay, remember polar, that's a term we use with covalent compounds, nonmetal, nonmetal. Okay, so polar solvents will dissolve polar solutes, polar covalent solutes. Polar solvents will also dissolve ionic solutes. Nonpolar solvents will only dissolve nonpolar solutes. Okay, so if water is polar, here's an example from your everyday life of a nonpolar solvent, oil. Okay, if any of you do a lot of cooking in your kitchen, okay, water will dissolve table salt because table salt is an ionic compound. Okay, oil will not dissolve table salt. Okay, so if you have a pan of olive oil on the stove and you throw in some sea salt or kosher salt or something that you're doing cooking with, those salt crystals will not break down. They will just stay in solid form. However, if you were to throw in, like let's say again, you've got this pan of olive oil on the stove. If you threw in like a pat of butter into that pan, the butter will dissolve. Okay, butter has compounds in it that are non-polar. So the non-polar oil will dissolve the non-polar butter. Okay. So is water polar? Yes, and we're going to talk about water as our solvent a lot. And I hate to be the bearer of bad news, but guys, you cannot forget how to tell if a covalent compound is polar or not. If you guys will go back and look through your notes, when we had this big chart that had all of the different shapes on it. Remember, like tetrahedral, trigonal planar, those kind of shapes? There was a column on that chart that indicated what shapes are polar or non-polar. You can't forget how to determine if something is polar or non-polar. Okay, because we've already learned that. So if I throw a covalent compound at you, I'm going to assume that you're able to tell me if it's polar or not. Okay. So actually, let me back up. So at this point, if you look at the homework questions associated with this sheet of notes, you are at this point able to do questions 1 through 17. Okay. Actually, no, scratch that. Let me go one slide further. Okay. You have this exact same graph on your notes, exactly the same. Okay. This graph is what's called a solubility curve. And what they show for each of, you'll notice there's multiple different compounds on here. These compounds would all be solutes. Okay. This graph is showing you the maximum amount of these solutes that you can dissolve in 100 grams of water. Okay, you've got temperature on the X, but look at what's on the Y. Solute per 100 grams of water. How much solute can you dissolve? Okay, a little bit more vocabulary here. If we say that a solution is saturated, that means you have dissolved as much solute as you possibly can. If I add more than that, let's say I've saturated a saltwater solution, if I add more table salt to this solution, it's not going to dissolve, it's just going to start piling up at the bottom. That's what saturated means. If a solution is unsaturated, that means you haven't saturated it yet. Okay, you could still add more and it would dissolve. Okay, so sorry, now at this point I want you to pause this presentation, and now in those homework questions you are able to answer questions 1 through 17 at this point, and then come back. All right, let's look at these solubility curves in a little bit more detail, okay, because you will be asked to interpret these graphs, okay? So we talked about what a saturated solution is, what an unsaturated solution is. Let's talk a little bit about what a supersaturated solution is. The definition says a solution that is containing more than the maximum solute at a certain temperature. So here's the situation. Let me get my drawing tools here. And let's say that we are looking at, see if I can get this to work. Potassium nitrate there, okay? And let's say that I saturate it at 65 degrees, so that's like right there. Okay, so if it's at 65 degrees, I'm going to put a dot on that line right there. So a saturated solution of potassium nitrate, if I'm at 65 degrees, means I can dissolve about 120 grams of potassium nitrate. But let's think about if I have it at 65 degrees, but then I put this solution into the refrigerator. Let's say that the refrigerator is, I don't know, I'm going to put a dot right there, at, 17 degrees Celsius. Okay, like right there. Well, at 17 degrees, this potassium nitrate solution, it can only hold 30 grams of dissolved potassium nitrate. So in theory, if I started here and I have this saturated solution and then I put it in the refrigerator and it cools down, okay, and now it can only hold 30 grams. 120 minus 30, that means 90 grams of potassium nitrate would be piled up at the bottom of my beaker. Okay, I go to check on it when it's cooled down to 17 degrees, and I would see 90 grams of potassium nitrate piled up at the bottom of my beaker. However, if you cool it down slowly enough and in very careful conditions, sometimes, even though it would have cooled down to 17 degrees, it still would have 120 grams dissolved in it. Now, guys, that is a really delicate situation. Okay, it's very unstable. I could do, if I just so much as like touch the beaker, like just bump it, that would be disturbing it, and probably all 90 grams of that dissolved potassium nitrate that really shouldn't be dissolved is all going to come out of solution. So a supersaturated solution is a solution holding more dissolved solute than it really should at that temperature, but it's a really, really unstable situation. Okay, again, just touching the container can cause all of that dissolved solute that really shouldn't be dissolved to precipitate out. So that's how you make a supersaturated solution. So let's look at this. It says, how does temperature affect the solubility of a solid solute? Well, guys, I will tell you that every line on this graph that has a positive slope is a solid solute. So pick any one that you like that has, oops, let me go back. Pick any line that you like that has a positive slope. I mean, ammonium chloride, potassium iodide, potassium nitrate, sodium nitrate, all of these are solid solutes. So think about it. As temperature goes up, the solubility increases. For those of you that are coffee drinkers or tea drinkers, if you like your coffee or tea to be really, really sweet, you should have hot tea or hot coffee rather than iced tea or iced coffee, because you can dissolve more sugar in a hot drink than you can a cold drink. So temperature and solubility for a solid solute have a direct relationship. However, how does temperature affect the solubility of a gaseous solute? Any line on this graph that has a negative slope, HCl, ammonia, sulfur dioxide, those are gaseous solutes. So as temperature goes up for those, I can't dissolve as much. If you think about it, this is why we keep sodas in the refrigerator. I mean, aside from the fact that we like to have cold drinks typically, or like our sodas cold, we also keep them cold because more carbon dioxide will be dissolved, and so they'll be more carbonated. We typically like our sodas to be well carbonated. We don't want them flat. So a gaseous solute has the opposite effect with temperature. So, actually, I just answered that question. So the reason that gases don't dissolve as well at higher temperatures is because the higher the temperature, the greater the kinetic energy is of both the solute and solvent. And these gaseous solutes actually get physically kicked out of the solution. So the gas molecules move fast enough, they have enough energy that they actually escape. This is just showing you that as temperature increases, the solubility of a gas will decrease. If you look up online something called thermal pollution, this is a situation that has to do with the solubility of gases. People have issues with nuclear power plants because it causes the temperature of the bodies of water nearby to go up. And you might think, well, who cares? You know, who cares if the river next door to the nuclear power plant gets hot? Well, how do fish breathe? Fish breathe dissolved oxygen. If the river that they're swimming in is hotter, there will be less dissolved oxygen and the fish suffocate, essentially. So thermal pollution is not chemical pollution. Okay, people don't typically have issues with nuclear power plants because they feel like nuclear waste is being dumped into the rivers. It's because of thermal pollution that people tend to freak out. It kills aquatic life. And they get into fights with the coal industry, but the coal industry has their own issues. So anyway. I won't go into this, but if you Google this lake that's in Africa, Lake Nyos, there's a really tragic story that goes along with the village of people that lived around that lake, and that also has to do with the solubility of gases. So let me just go back for a second. There are questions in your homework, okay, questions 22 through 32, that have this exact same solubility graph, and it's going to ask you questions interpreting different solutes on the graph. So what I would suggest now at this point is to pause the presentation, complete questions 22 through 32, and then come back. Okay, so the last piece in this first part has to do with putting a number on how concentrated or not a certain solution is. If you say that a solution is very concentrated, that means it has a lot of solute dissolved in it. Whereas dilute means it doesn't have that much solute in it. Think about Kool-Aid. Okay, you make Kool-Aid with that powdered mix. Some people like their Kool-Aid really concentrated. Like they like a lot of the mix in there. They like it so sickly sweet. Other people don't. Other people like a little bit of mix in there, but not so much. They like theirs more dilute. Okay, these are relative terms. Can you put a number on how concentrated or dilute something is? Yes, you can. The most common method of measuring how concentrated or dilute something is a term called molarity. Molarity, which has a unit of a capital M, is calculated moles of solute divided by liters of the whole solution. Okay, or you can call that total volume if you like. Okay, let me change colors here. So if you look at just this simple example problem, it says, what is the molarity of salt water made with 125 grams of sodium chloride in a 2-liter solution? Okay, well, the first thing I know I've got to do is I've got to turn these grams of solute, I've got to get that into moles. Okay, the molar mass of sodium chloride off the periodic table is 58.5, I think. Okay, let's get a number for that. 125 divided by 58.5. And this is not my final answer, so I'm not going to round too much. I get 2.13, I'll call it 7 moles of NaCl. Okay, and now I'm ready to calculate the molarity. So I'm going to bring that number up into the numerator there. So I get 2.137 moles, and I'm going to divide that by the volume, which was 2.0 liters. And now I'll round for significant figures. I want to round to 2 significant figures, so that gets me a final answer of 1.1, and you can just write the units as a capital M. Okay, and that's all there is to it. Sometimes you'll be asked to solve for the volume of the solution. Sometimes you'll be asked to solve for the moles of solute or maybe the grams of solute. Sometimes, just like this one, you're asked to solve for the molarity. But that's as simple as it gets. Okay. Let me do just a couple of practice problems with you. All right, so if you look over at your homework problems, let's see. Let's look at number 42. Okay, it says, if somebody gave me 200 grams of sodium sulfate. Okay, stop there. What's the formula for sodium sulfate? Think about swapping and dropping. Think about your charges. Okay, 200 grams of sodium sulfate, and I made a solution with a volume of 500 milliliters. What would the molarity be? Okay, well, just as before, guys, the first thing I got to do is I've got to get my solute out of grams and into moles. Okay, so the molar mass of sodium sulfate, 142.3. And again, this is not my final answer, so I'm not going to round too much. So that gets me 1.405 moles of sodium sulfate. Okay, and now I can solve for the molarity because I've got my number of moles. Okay, remember the volume has got to be in liters. 500 milliliters, that's 0.5 liters. And let's see, let's look at the original problem. I want to have 3 significant figures, so I'm going to round this to 2.81 capital M. Final answer. Okay, let's look at one more. Let's look at number 44. Okay, just 2 problems down. It says, how many liters of solution would you need if you wanted to make a 6 molar solution and all you had was 50 grams of aluminum bromide? Okay, first of all, guys, what's the formula for aluminum bromide? There it is. Okay. I can see that my aluminum bromide is in grams, and I got to get it out of that because moles are what's in the formula for molarity. So let's see, 50 grams. Aluminum bromide. Okay, the molar mass for that off the periodic table, big number, 266.7. Okay, let's get that into moles. So 50 divided by 266.7. 0. I don't want to round too much, 1875, let's say, moles of aluminum bromide. Okay, now this time I'm not solving for molarity. This time I was given molarity. So the molarity is 6. I have the number of moles. This time volume is my unknown. Okay, so we'll do a little bit of algebra here. And now I'm ready to round to, let's see, 2 significant figures. So I get 0.031, and that's a volume. Now think about what unit that volume is going to come out in. Liters. Final answer. Okay, so I just wanted to go over 2 just example problems with you. Okay, the very final portion of these notes, okay, have to do with factors affecting how well something will dissolve. Okay, how fast will it dissolve? It doesn't affect how much will dissolve. Remember, temperature is the only thing that can affect how much of a solute will dissolve, but there are things that will impact how fast they dissolve. Okay, one thing is stirring. Okay, if you are dissolving salt in water and you just dump it in and then let it sit there, it will dissolve eventually. but it'll dissolve a lot faster if you stir it or agitate it. Okay, temperature, as we said, can change the amount. It also can make it go faster. Okay, it also increases the speed at which a solute will dissolve. Okay, surface area affects it. And I've given the example here of granulated sugar versus sugar cubes. Okay, granulated sugar, ground up, crushed up sugar, has a lot more surface area than a sugar cube, so that'll dissolve a lot faster. Okay, so these are just some things that can affect the rate at which something will dissolve. Okay, so just to kind of, bring this all together. Solids, you increase the temperature, you will increase the amount that will dissolve. Agitation will increase the solubility. Okay, shaking it up will increase the speed at which it dissolves. Gases are the opposite. We're just summarizing here. If you increase the temperature, the amount of gas that will be dissolved will be less. Okay, and agitation has the opposite effect. Okay, think about if you shake up a soda. If you shake up a soda, that's going to cause the gas to come out of solution. That's not going to help it dissolve better. That's going to make it worse. When you shake up a soda and it erupts out of the bottle, that is the dissolved gas coming out of solution. So solids and gases as solutes behave in opposite ways. So guys, I know this one was kind of long. That is the end of the first lesson. It's a lot of concept, a little bit of math. So at this point, you now have the ability to answer any of the homework questions on the note sheet, and then you can check your answers. I look forward to seeing you guys in our next lesson. Take care, y'all.